Hey class, this is Mr. Schmidt, and now we're coming to you for our November 3rd recap of AP Physics, and we're looking at force diagrams, sketching them and using them to solve a problem set as we get ready to go into the kitchen scale of chemistry next week. Okay, first and foremost, this is the end of the quarter, which means any late work, any grade defense all needs to be turned in this week. So grade defense, this is your first wave at it. So the idea is that, let's say you missed your acceleration question on quiz 1, but you got acceleration right on quiz 2. You send me an email saying that, I double check it, I give you points on quiz 1. Another example, you missed the units on quiz 1, but you showed all your work on quiz 2, and in there you showed how displacement is meters and velocity is meters per second, and you every time you showed your work, you showed the correct units. Okay, you send me an email stating that fact. I look up all the work you showed, I can give you points back. Now, if you don't show your work on your test, there's no way to demonstrate that mastery. So that's why you should always be showing your work. Another reason, okay? All right, so other thing coming up here, we're going to be using kitchen scales in the following week, okay? Trying to find my kitchen scale here. So the idea is you're going to put something on here and you're going to elevate it, and elevator going down, and don't get on this elevator that's going left to right, okay? And then you're going to tell me what happens to the scale here as it moves around. So make sure you find access to a kitchen scale, or you text me so we can find a solution for you to do this lab in the next week. Okay. All right. So let's turn the page here. We had a warm up of how many people do you think it would take to pull down the Eiffel Tower? Okay. People looked up a lot of stuff, starting with how much did the Eiffel Tower weigh and how much force can a person pull with. One person brought up, at least one person brought up a nice example of tipping it over. This is from Penn State University's mechanics division. And they look at, when you push on something, two things are going to happen. Either it's going to slide due to friction, or it's going to tip over. Okay, still due to friction, but then it's going to act as a lever rather than as a sliding block. Okay, so the question for us is, with our Eiffel Tower, depending on where you attach the ropes and how much force was applied, which would these occur? Almost everyone assumed a tipping force. It seems like a lot of people even assumed picking up the Eiffel Tower, like, if it weighs this much, we must be able to apply enough force to lift the entire weight, which is not necessarily going to be the same as overcoming the friction force. Okay, so this would be how we'd go through friction. But as we look at tipping, what we see is these different forces moving, and instead of the force being spread evenly across the entire object, it gets centered along the corner, and that's where the tipping occurs. Okay, so the reason why I chose this question is because I wanted us to start looking at drawing forces. Okay, so for answers, by the way, people were getting about 200, 300,000 people to pull over the Eiffel Tower. Okay, so that was kind of the ballpark numbers I was looking for, that 10 to the 5th, 10 to the 6th type exponents. All right, so next up, we're looking at some forces here and Newton's laws. This is a classic horse and cart question. One physics textbook I used years ago had a conceptual question saying, if you hooked up a horse to a cart, and the horse was a physics student, and they said, well, for every action, there's an equal and opposite reaction. So if I pull on the cart's going to pull on me with an equal and opposite force, and therefore, neither one of us are going to move. Okay. The fact is, there is a force pulling on the horse and a force pulling on the cart, which are equal and opposite, but that does not translate into motion, because or have any impact really on motion, because we don't want to look at this action-reaction force. We want to look at all the forces that are acting on one system. So if our system is this wagon, we need to look at all the forces that are acting on this cart. Like the horse is pulling on it, friction is opposing motion, gravity is pulling down, the floor is pushing up. Those are the forces we want to start drawing in our actions and reactions and in our force diagrams. So the first example I gave was a ball on a ramp, okay? So when we draw out these forces, the ball obviously could roll, gravity is gonna act down, the ramp is gonna push up perpendicular to the surface, and then any friction opposing motion will also pull as well. So we get something fairly similar to this, of the weight, mass times gravity being down, the normal force, okay, pushing off to the side, and then an applied force opposing motion, which is going to be the force of friction, okay? And then here we have a component of the weight as well. So we see they've split the weight into a Y component and an X component, only they've shifted their coordinate plane as well, okay? So when we look at drawings like that, we see there's a few different forces that keep appearing over and over again. Gravity is almost all of our questions. We're going to be acting on Earth for every question we see this unit. So we're going to have mass times gravity operating straight down, okay? No bending. It does not matter what you do with the ramp or if you're on a loop or anything else. We're always going to have the force of gravity pulling straight down, okay? That's different than the normal force. The normal force is what is pushing up with the surface. So you're at the table or the floor or the ground, whatever's pushing up, that is the normal force, okay? So it's gonna keep pushing up until, you know, the table breaks or something like that, okay? And if we're looking at a ramp, as the ramp bends, we're still going to have the normal force is always going to be perpendicular to the ramp, okay? So that is the normal force. If we have any ropes or chains or string or cables or anything like that, that will have a tension force, which is going to be a big part of Friday's discussion. And then if there's any opportunity for this object to move, there will be friction opposing the direction of motion, okay? And here we see more equations. Right now, we're just worried about the drawings. Okay, so let's take a look at a few different drawings as we go up through these. All right, so the first one, the simplest one, we just have a box on a flat surface, and that box is moving, okay? So we're gonna have a velocity, okay? The magnitude of this is not very important. Remember, this is not telling us acceleration. This is only telling us velocity. So that is not necessarily gonna affect our forces or the magnitude of our forces. Okay, so we have some things that we're going to have right off the bat. Okay, and then we're going to have our force normal. Okay, now this is moving this way. The reason why I wrote that down is because that means the force of friction is going to oppose that motion. And then if there's a motor or a rope or a chain or anything causing it this way, we might have an applied here. Okay, so if this is our scenario, then if we have an initial velocity, in order to find out acceleration, we're going to have to use Newton's laws. Okay, so we're going to sum the forces in the x to find out our acceleration in the x, and we're going to sum our forces in the y to find out our acceleration in the y. Now, it'd be very unusual for these to add up to anything other than 0, okay? Normally, if you put something on a table, it stays on the table. The table does not break. It does not fly off the table. So all of our scenarios we're going to start with, these two are going to add up to 0, okay? All right, However, this one very rarely adds up to 0. So if we're going to look at that one again, we would see that the force in the x is going to equal our force applied plus our force of friction. Now this is going to be a negative number, but when we're listing out the different components, we are adding the positive to the negative, okay? And that will tell us our acceleration in the x. Now, the other thing we'll also see is a number of times they will give us this number and we will have to solve for mass, okay? So it'll be important for us to remember that mass equals the force of gravity over g, okay? So we'll see that quite often is that the number will be given in this diagram and then we're expected to deduce the mass, which we can then apply to find here. Okay, so this is our simplest scenario. What happens when things get a little more complicated here? Okay, now we have our box going this way. All right, so our forces, we still have the force of gravity going straight down. Okay, normal force is still perpendicular to the surface. Okay, now again, well, let's start with like saying this. If force of friction is going that way, then that implies that velocity is moving this way, okay? So these are going to oppose each other, okay? And then sometimes you'll have a motor or a string pulling it down, but frequently, if you put something on a ramp, gravity is the only thing pushing it down, so that the more you increase the incline, the more gravity is acting in the same direction as this, and it will give us our new number, okay? We'll go more about the fact that our coordinate plane does not always have to sit like this. We can take our coordinate plane and call this x and call that y as we go through these to make our math easier. But today we're just doing our drawing, so we can stop right there, okay? And in terms of drawings, I also did one of the homework questions, okay? Now, I'm a physics teacher and not an artist, so this is my dog, okay? The dog was on a leash, okay? So we had tension or a force on the string from the leash, okay? Again, force of gravity pulling down, force normal pushing forward, okay? The dog was traveling in this direction, okay? Therefore, there must have been a force of friction acting this way. And then the dog itself was pushing on the ground, so we have a force applied that way. These are our forces in the force diagram. Now, if it comes time to do those numbers where we sum the x and we sum the y, then we're going to want to break this up into an x and a y. So we would take that tension force and we would want to find an f of x and an f of y, okay? So that when we did those sums, it's going to equal this one, okay? So we could call this from the tension, okay? And what else did we have in the x? Okay, the tension was pulling this way, the force of friction was pulling that way, the applied force was pulling in the same direction. Again, some of these would be negative, some would be positive, okay? In this case, I expect the dog could very easily have acceleration. Now, if you pull on the chain really hard, dog might accelerate backwards. If you let slack on the chain or the leash, the dog might be accelerating forward. So we are not going to know this until they give us numbers. But right now we're just looking at our drawing. Okay, and again, if we're trying to look at the f of y, okay, that would equal our force of gravity plus our force normal plus our force and the y from the tension. And again, this almost always equals 0. But what happens if your dog runs into the highway and you just rip on this leash as hard as you can and the dog comes off the ground, right? Well, now we have a non-zero acceleration, okay? And once again, if they don't tell you m, then we can solve for it by taking our force of gravity divided by 9.8. That will give us our m. Okay, so those are the beginnings of the assignment. Okay, and like I said, this was taken straight off of the dog pulling on the leash drawing. So you're just going to add in all the arrows. You don't have to worry about adding anything up yet. So this is going to go super fast. Okay. So then you will have a second assignment that will look at more at Newton's second law, F equals ma. So there will be some adding, but right now we're doing the drawings as one assignment and the calculus and algebra as a second assignment. As we get towards the end of this week, we're going to be putting those things together, but I want to make sure we understand those independently before we get them going too far. Okay. Once again, later this week, you're going to want a kitchen scale to get everything done. So start collecting your materials now or reach out to me if you need any help. Okay. And with that, have a good day. Have a good afternoon.